Okay, we're going to do some examples of drawing Lewis structures for covalent molecules. So let's start with a very simple one, H2. So first step was to count the number of valence electrons in the molecule. So there's 2 hydrogens, and each hydrogen brings 1, so it's a total of 2. So then you place your atoms, step 2, and then you place 2 electrons between each bonded atom. So you can do it as a dash, or you can do it as 2 dots. So there's our 2 dots. Now we have used up 2 electrons, so we would subtract this 2 from the original 2, so we have none left over. So we have satisfied the octet rule in terms of hydrogen. Each hydrogen only wants 2 electrons in total. This hydrogen now has 2 electrons around it. This hydrogen now has 2 around it. So they're both content. So our Lewis structure is correct. And the alternate was that. Okay, F2. There's 2 fluorines, and each fluorine brings 7. So we have a total of 14 valence electrons to place. So that's step 1. Step 2, place your atoms. Step 3, put a bonding pair between them. So you either put it as a pair or as a dash. So now I have 12 electrons left to place, because step 4 says subtract the number of bonded electrons from the total. So step 5 says arrange them around the terminal or outside atoms to satisfy their octet rule. So the fluorine on the left currently has 2, so it needs 6 more. 1, 2, 3, 4, 5, 6. And the fluorine on the right has 2, it wants 6 more. 1, 2, 3, 4, 5, 6. So I've satisfied the octet rule of the fluorines. I've used 12 electrons, so now I have none. So fluorine has the combining capacity of 1. It makes 1 bond, which it did, and then the remaining electrons were placed around it. So in total, we have used 2, 4, 6, 8, 10, 12, 14. And we had 14. So we did it correctly, and each fluorine is surrounded by 8 valence electrons. So we know that these structures are correct. And I expect you to show this work. Minimum, you have to show the total number of valence electrons calculated. Okay. H2O. 2 hydrogens bring 1 each for a total of 2. Oxygen, so that's H. Oxygen brings 6 valence electrons. Add the 2 and the 6 together and you get 8. So we have 8 to play with. So oxygen has a combining capacity of 2. Hydrogen has a combining capacity of 1. So oxygen goes in the middle. Now, hydrogen will be on the outside because it's a terminal atom. Put the bonding electrons between them. So we've used a total of 4 electrons. So we have 4 left. Now, we have satisfied the rule for hydrogen. They each have 2. So we're done there. So in terms of step 5, we're done. If there are leftover electrons, we put them on the central atom, and we always put them in pairs. So this is now step 6. We've got 4 left over, so they go on the central atom. So we have no more electrons left to place. Let's see how many we've used. 2, 4, 6, 8. So we only had 8 to start with, so that's good. Hydrogen surrounded by 2, that's good. That's good. Oxygen is surrounded by 8, that's good. And we haven't broken any combining capacity rules. So oxygen, hydrogen, hydrogen, 1, 2, 3, 4. But I want you to get into the practice of drawing this as a bent structure. 1, 2, 3, 4. Water is not straight from hydrogen to hydrogen. The lone pairs of electrons actually take up more space than bonding pairs. All right, let's do another example. We're going to do carbon dioxide. So carbon brings 4, 2 oxygens bring 2 times 6. So we've got a total of 16 electrons to place. Carbon has a combining capacity of 4, oxygen 2, so carbon goes in the middle, and you put the oxygens on either side. Now, place bonding pair between them. So we've used up 4 electrons total, so we have 12 left to place. So, complete the octet on your terminal or outside electrons. So we're up to step 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've used a total of 12. So we have none left. All right. So if we look at oxygen, oxygen surrounded by 8, that's happy. This oxygen is surrounded by 8, that's happy. Carbon, however, is only surrounded by 4, and we have only 1 bond between each of the oxygens and the carbons. So this is not good. So step 7 says, if your central atom doesn't have a full octet, convert one or more lone pairs, to a double bond. So what we're going to do is we're going to take one of these and put it between. And we're going to do the same thing on the other side, because that will allow us to increase our number of bonds. So this is going to become a bond, and this is going to become a bond. So what happens is you end up with this. So let's check this out. 2, 4, 6, 8, 10, 12, 14, 16 electrons placed. So we've used all the electrons we had. Oxygen surrounded by 8, oxygen surrounded by 8, and now carbon has 8 because there's 2 electrons in each one of those bonds. So now we have the correct Lewis structure. We've used 16 electrons. Everybody's octet is complete. What happens if we have a negative ion, like nitrate? Nitrogen brings 5. 3 oxygens will bring 3 times 6, so 18. If you have a negative charge, it means you've got an extra electron. So that -1 charge means you add in an electron. So 19 and 5 is 24. So we have 24 electrons total to place. Nitrogen's combining capacity is 3. Oxygen's is 2, so nitrogen goes in the middle. So put in your central atom. surrounded by the other atoms, and put a bonding pair between them. So we have used a total of 6 electrons, 2 in each one of these bonds, so 2, 4, 6. So that leaves us with 18. So satisfy the octet around the terminal atoms. So each one of these oxygens has 2. We need 6 more for 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have used 18 electrons. We have none left over. So we have used 8, 16, 24, which is all we had. Each of these oxygens is surrounded by 8, but nitrogen is only surrounded by a total of 6. So we have to take one of these oxygens and make a lone pair into a double bond. So however many electrons you're down, for every 2 electrons you're down, you have to make an extra bond out of a lone pair. And we'll see this a lot on oxygen. So we have to redraw our Lewis structure because now we have a double bond. So 2, 4, 6, these didn't change, and now we only have 2 lone pairs. So let's double check. 8, 16, 24. So all your oxygens are surrounded by 8. We've used the maximum number of electrons, and nitrogen is now surrounded by 8. So this is good. The only thing we have to add when we have an ion is square brackets and a negative charge. In this case, if it was positive, we'd put a positive charge. Okay, let's do this example. It's an example of an ion, but a cation. So 3 hydrogens bring 1 each, so that's a total of 3. Oxygen brings 6, so that would be 9 total. But the +1 charge means we lost an electron. So we have a total of 8 valence electrons to place. Oxygen has a combining capacity of 2, oxygen 1, so we know oxygen is in the middle. Okay. So each one of these bonds is 2 electrons, so we've used a total of 6. So we have 2 electrons left to place. Each oxygen only requires 2, and there's 2 in every bond, so they're finished. So we have extra electrons left over. So following step 6, they go on the central atom. So now I've used up this 2 electrons. So in total, I had 8. I've used 2, 4, 6, 8. So I don't have any more left to place. Each hydrogen is surrounded by 2, so that's good. And then oxygen is surrounded by 8. 2, 4, 6, 8. So the only thing left to do is to put square brackets around it and give it a +1 charge. Okay, so fluorine, using TVS method. So T, we have 2 atoms, and they both want 8 around them altogether. They want to satisfy the octet rule. So that's 16. Valence, we have 2 fluorine atoms. They each bring 7. So that's 14 total. So if we subtract 14 from 16, we get the number that are shared, which is 2. Divide that by 2 and you get the number of bonds. There's only one bond. So F, F, with one bond in between it. So we've used 2. So now you have to go back. So this is partially like the other method. We've got 14 valence electrons in total. We've just used 2 in the bond. So now place the electrons to satisfy your octet rule. So now we had 14 minus 2 is 12, 12 valence electrons. We've just placed them around fluorine. So if we double check this, 2, 4, 6, 8, 10, 12, 14, cannot exceed that number, and each fluorine is surrounded by 8. So we know this is the correct structure. So that's good. All right, water, H2O. So the total around oxygen will be 8. It wants 8. And we have 2 hydrogens, and they will want 2 around each other, around each of them. So this is going to be a total of 12. So this is how many they want around them all together, multiplied by the number of atoms of that type. So oxygen wants to be surrounded by 8. Hydrogen wants to be surrounded by 2, and there happen to be 2 of those atoms. So now valence electrons. Well, oxygen brings 6, 2 hydrogen brings 1, for a total of 8. So if we subtract 8 from 12, we get 4 shared electrons. Divide that by 2, and we know there's 2 bonds. So oxygen and 2 bonds. Oxygen is in the middle because it's got the highest combining capacity. So we have our 4 electrons placed in bonds. So we subtract 4 from our 8 valence electrons, which leaves us with 4. Hydrogen is satisfied, so the extra 4 go on oxygen. So let's double check our structure, because you always should. Each hydrogen is surrounded by 2. Oxygen is surrounded by 8, and I've used 2, 4, 6, 8 electrons, and that's the maximum number I can place. So this structure is good. So CH4, methane. Total. Carbon wants to be surrounded by 8, and we have 4 hydrogens, and each one of them wants to be surrounded by 2. So 16 total. Valence. Carbon brings 4, hydrogen brings 1, for a total of 8. Subtract 8 from 16, and we get 8 shared. Divide that by 2, that means 4 bonds. Carbon has a combining capacity of 4, hydrogen 1, so carbon is in the middle. Place your bonds and your hydrogens. So we have used up 8 electrons in our bonds. We don't have any left over. Let's double check our structure. 2, 4, 6, 8. 8 total used. Each hydrogen surrounded by 2, and carbon is surrounded by 4 bonds containing 2 each, for a total of 8. So that structure is correct. All right, let's do a trickier one. The beauty of this is that it really helps when you don't know what the structure is. So let's say we have COH. 2. So T. Carbon wants 8. Oxygen wants 8. You have 2 hydrogen that wants 2. So 8, 16, and 4 is 20 electrons. Valence electrons. Carbon brings 4. Oxygen brings 6. 2 hydrogens bring 1 each, for a total of 12. So when you subtract these, you get the shared. So 8 electrons are shared, or there's 4 bonds. Carbon is in the middle. So if you do this, we can see that we've only got 3 bonds. Hydrogen can't make any more, but oxygen can. So there's your 4th bond. So now I've made my 8. I've got 4 left. Sorry, that's an equal sign. I've got 4 left. Carbon can't take any more. Hydrogen can't take any more, but oxygen can. So now let's double check our structure. Hydrogen 2, carbon 8, oxygen 8, and I've used 2, 4, 6, 8, 10, 12 electrons. And I have 12 maximum. So this method works nicely because it does tell you how many bonds or dashes you should have in your structure. Okay, so I'll do one of the ions. TBS. So total. We have 3 hydrogens, and each one wants to be surrounded by 2. And we have an oxygen that wants to be surrounded by 8. So 6, so we want 14 electrons in total. Valence electrons, 3 hydrogens and 1 oxygen, but don't forget the charge. It's 1 plus. And what you do is you subtract 1 for each positive charge. You would add if this was negative. So we're going to subtract 1 as well. So 3 plus 6 is 9, minus 1 is 8. So shared, we have 14 minus 8, which is 6, or 3 bonds. Oxygen has the highest combining capacity. So we put that in. We have now used 6 electrons. So we're going to subtract 6. That leaves us with 2. Hydrogen is happy, so these are going to go on our central atom. So now, hydrogen, 2 each. Oxygen now 8. We have used 2, 4, 6, 8 total. We have 8 total. So the only thing you would have to do is put square brackets and a charge. Now, this is called the hydronium ion. And it's important in acid chemistry. So we'll get this when we get to acids and bases. And basically, no pun intended, it is an example of a coordinate covalent bond. So a coordinate covalent bond occurs when one atom donates both electrons to a bond. So a coordinate covalent bond, one atom donates both electrons to a bond. So here, what happened was we had water with its two lone pairs. Along comes a hydrogen ion with no electrons on its own. It's positive because it lost that one electron that it had. So what happens is a lone pair of electrons can make a bond and offer itself up to the H plus ion, and we end up with 3 hydrogens bonded, and that net positive 1 charge is because of the positive charge on that incoming hydrogen. So that is a coordinate covalent bond. Instead of sharing, each one bringing some electrons, basically what's happened is one electron donates them both. So you have to have lone pairs of electrons in order to do that. The two atoms that do this most are nitrogen and oxygen.